In this lesson, we'll introduce the HR analytics case study. The case study has the following 5 segments of analysis. First, we have to analyze the recruitment data for various sources of recruitment and their effectiveness in terms of sales quota percentage, attrition rates, among others. Next, we carry out engagement analysis across departments and job mix levels. We also try to find the relationship between disengagement levels, salaries, and vacation days taken. In the next part, we examine the pay data for fairness in salaries. We also examine pay differences across different job levels, gender, and different departments. We also compare the performance evaluation of employees to see if there is any bias across genders or different job mixes. Lastly, we'll conduct employee safety and accident data analysis, and we'll try to find if there is any relationship between accidents and levels of disengagement and vacation days taken. In this video, we'll introduce the case study on HR analytics pertaining to training and development program in an organization. To begin with, as an HR consultant, one of the Fortune 500 companies have invited you to understand employees' needs, improve employee safety, understand and improve employee fairness and diversity, identify drivers of employee attrition, and also identify the best recruiting sources and check whether the workload of employees are appropriate. The company has collected data on following parameters, including recruitment firm survey, employee engagement survey, salary survey, gender survey, performance survey, accident survey, and location survey. In subsequent parts, we'll discuss the individual assignments related to each survey. In first part, you are expected to do recruitment data analysis. Here, you are expected to analyze the data by performing the following tasks. First, you have to import the recruitment.csv file, then find the number of hires per recruiting source. You are expected to find what recruiting source provides the best performing salespersons and also visualize the data. You're also expected to find which recruiting source salespersons have the lowest attrition rates and also try to visualize the data. Lastly, you're also supposed to provide precise and sharp inferences from these results. From this video, we'll start with our case study analysis exercise. First, we'll set the working directory, add the libraries, and load the data. So as a first step, we'll set the working directory, session tab, set working directory, choose directory. Now here we'll set this directory. I'll copy this location for future reference. This is the place where I've set the working directory, and if I've done everything correct, on the files tab, all the relevant file that I want to use in this particular exercise will be appearing. The next step is to add the relevant libraries. In this particular case, I want to use this tidyverse library. This is the only important library for now. So we'll add this library. The library is getting loaded. The next step here is to I'll zoom in a little bit and then load the data. Now in this case, in the part 1, we want to conduct recruitment analysis. So this is our part 1 where we want to conduct the recruitment source analysis. So first we'll load the recruitment data, which is here. So we have the recruitment data with us. So we'll load the data, import data set. Now, once you have this recruitment data, it will appear like this. So let me just copy paste this command. So I've loaded the recruitment data for future reference. If I've loaded this data correctly, first and foremost, let me show you a few parts. So we'll see the glimpse of this data with this glimpse command, and I'll make the name as recruitment for simplicity's sake, recruitment. So if I show you the glimpse command, you can see it has 446 rows. That means 446 values along with the 4 columns: iteration, performance rating, sales quota percentage, and recruiting source. So to summarize this video, we have set the working directory, added the tidyverse library, and loaded the data. We have briefly summarized and seen the overview of the data that has 446 rows and 4 columns, and the variable attrition, performance rating, sales quota percentage, and source. Attrition is, as the name suggests, attrition rate, their performance ratings, how much sales quota percentage they have achieved, and what is their recruitment source. So we have added these information variables that we are going to use in the analysis of the data. In this part, we'll carry on with our analysis of recruitment source analysis. First, we'll try to answer the question, that is, find the number of recruits from each source. Now to answer this question, we will again go back to our recruitment data set. In this recruitment data set, first we'll count with the source, so recruitment. Now to count, one approach would be to apply this count command and recruiting source. Now if I run this, you can see here, so the maximum have come from this source which is not available. Applied online is 130, and then campus 56, referral 45, search firm 10. Another approach would be to use this table command that also you can apply. So you have recruitment data dollar recruiting source. So this is also the same way to achieve the same output. You'll have search firm, but here you don't have the NA source, which has 205 observations, but other you can see applied online campus 45, the data matches. Now the next question we in the recruitment analysis we are going to answer is that which recruiting source results in hires that attain highest sales quota percentage. Now let's again analyze our data. So one way to do this is first use our recruitment variable recruitment. Now we'll filter it step by step. So first, the first filter is to use group by. So first we'll group by the data with recruiting source. We'll group by. So if I print it, you can see the data is now grouped with recruiting source. The next step would require summarizing our data. So we'll use this summarize command. And inside summarize, we'll use average sales quota percentage. Average sales quota percentage. So this is our summary variable, and this variable will contain the mean values of sales quota percentage. So it will carry the mean values of sales quota percentage. So for example, if I print it, you can see the mean sales quota percentage are printed. The last thing would be for a better representation, let us arrange the data. So we'll arrange the data in probably ascending or descending order. Let's say we use descending order, for example, and put our average sales quota percentage data. So we have arranged them, and I can print it. I need to just correct the spelling. You can see it has been arranged, and you can see the maximum that has been achieved by NA, and then the lowest is by search firm and so on. If you want, you can sort of use this one variable called average sales. Probably you can give them average sales name and save it also. So now it is much easier to print it in future. Now, if you want to analyze this data, one can comment that those in NA bracket probably who are lateral hires, who are probably know in the business for many years, they are in the business, they know, and so they can directly apply or through connecting through some common connect like LinkedIn, meeting senior people and getting the hire. And probably these are the people with much more relevant experience, and that is why you can see they are able to do well. So that justifies their recruitment source and their higher sales quota percentage. Now, the next question that we would like to answer is which recruiting source results in highest that attain the highest percentage at lowest or highest attrition rate. So we are interested in the attrition rates. So we'll try to answer which recruitment sources results in hires that attain highest attrition rates. Again, important data that we want to have. So very simple. So we'll again go back to our recruitment variable. Inside the recruitment variable, with this pipe symbol, we are going inside the recruitment variable, and we are again grouping it by the recruiting source. So we are grouping it because the focus of analysis is recruiting source. So we are keep going back there again and again, and then again use our good old summarize variable. But now we are interested in the attrition rate variable. So we'll use this attrition rate, and it will be equal to mean of attrition. We'll have this mean of attrition, and again the same arranging the data. We'll arrange it, but arrange it maybe descending order would do with the attrition rate variable. So now because our interest is in attrition rate, so you can see the attrition rate. As you can see, the again the lowest attrition is with NA while highest is with the search firm. So you can see those who are coming from search firm, they are not doing well, or even the referral guys are not, whether it is sales quota percentage or this search firm is the lowest. So they are not doing well. So search firm guys who are coming from search firm have the highest attrition rate. But again, interesting feature, those who came from sources not available, the same kind of lateral hires, maybe from LinkedIn or from some common connect, who have been in this industry for many years and they have the experience, relevant experience, and they are performing well, got through some common connect based on their previous performance and experience, got selected. They have low attrition rates also, probably they are more successful and happy, and so on. In fact, you can, if you want to save this, you can just save this average attrition variable and you can save it here and you can print it, average attrition. So you can print it, you'll get the same output again. In the last leg of analysis of this recruitment source data, we would like to visualize our data, and we would like to visualize our attrition and sales quota percentage data. We'd like to visualize them. So it is pretty simple. Already we have created our average sales variable. So we'll use our ggplot command and we'll specify our data. Our data is average sales. So this data we are going to visualize. And inside this data, we are going to specify our aesthetics arguments. So we are comfortable now with the ggplot. So I can do that. So first is the recruiting source on x-axis, and on y-axis, I can put average sales quota percentage data. So these are our data point that I want to visualize. And if I press enter, you'll notice nothing will be plotted, just an empty plot will appear. So I need to provide some more information, particularly what kind of geometric object I want. So I probably for now I'll use the column kind of objects to visualize my data. And in aesthetics, I'll specify the color will equal to recruiting source. So this would be sufficient for plotting. So if you can see, I have plotted it. Now very interesting graph has appeared. You can see all the colors and average sales quota percentage wise. The same data, you can see those coming from NA not available search firm, they are the highest, and those coming from search firm, they are lowest. Now, if I want to make the attrition plot, I will not rewrite the code. I'll simply just use the same code, and instead of average sales, I'll just use my attrition variable. Now inside that attrition variable, I have to just change this particular variable to attrition rate now. So I'll change this variable. I'll show you the full code. So I need to just change it to average attrition. Sorry, attrition rate, average attrition, my variable. So it has to be attrition rate. So this is there. And lastly, this attrition, this recruitment source remains the same. So now I'll plot the data and let's see in terms of attrition rates, how my plot appears. Again, similar plot, but with different data points. So you can see the lowest attrition with not available sources, the same lateral LinkedIn kind of hiring, and the highest from search firm. So to summarize, in this video, we analyzed the recruitment source data. We found that those coming from the search firm are not only performing poorly on the sales quota percentage, and they have the highest attrition rates. And in contrast, those who are coming from lateral kind of hires like sources like LinkedIn are doing better. And in terms of attrition rate also, they are low and their sales quota percentage is also higher. In the second part of this case study analytics, we are supposed to do employee engagement data analysis. Here, we are expected to analyze the data through visualization and performing the following tasks. First, we'll import the survey data file and find the number of employees from each department. We'll find the average engagement score for each department and also classify those scores with 0, 1, and 2 as disengaged. We'll find the department-wise average salary and vacation days for the disengaged employees and also visualize the data. Next, we'll examine whether the differences in engagement and vacations are statistically different in the sales department vis-a-vis other departments. Lastly, using these results, we'll provide precise and sharp inferences about the link between engagement and business outcomes. In the second part of this case study, that is part 2, we'll try to answer the question, that is, what is driving low employee engagement? Low employee engagement. So for this, the first question that we need to answer is, we need to import the survey data. So we'll first import our survey data, and for that we'll go to the survey data, we'll import it. So our survey data is imported. For reference, we'll have a copy of this data file, survey data. Now I'll slightly modify it for my requirement. So I'll just use this, read the data, and just call it survey. So this is my data that is read. If you want to know more about this data, you can run this glimpse command and do this survey thing. So you can see there are 1470 rows. That means observations. Employee ID is there, their department, sales, engineering, is mentioned. So there are department names in character format. Their engagement levels. So their scores, engagement scores on scale 1 to 5. Lower scales means probably they are disengaged. Their salaries are mentioned and their vacation days taken. That is also mentioned. So let us start with our exercise. The first thing that we need to answer is we need to count the data. So we need to count the employees from each department. So for the counting thing, it's very simple. We need to run this survey data, and all we need to do is we need to just count. We need to apply this count by department. So this will give us a count. We can see from engineering department there are 961. So most of them from engineering, some from sales, and then finance 63. The next question is we need to compute the average engagement scores of across the departments. So in the next part, we need to compute the average engagement scores across departments. So this is again not very difficult question. We'll just run our survey data. We'll use this pipe symbol to go inside the data, group it by department because we need departmental kind of summary. So we'll group it by department. Then further go inside. Now that we have grouped it, we'll summarize it. So we'll summarize, and inside survey we'll create another variable, average engagement. So this average engagement variable is created and we'll put the average score of engagement variable. So this should suffice. Although I can use this, but let us further improve upon it like we have been doing. We'll arrange our data. So we'll use this arrange command, and in a descending order that would probably helpful, and then average engagement. So we'll use this, and now I'll just use this average engagement equal to me. So probably I've done. So I'll just small mistake was there. So I'll just now print the data, and you can see it is in arranged descending manner, and you can see the average engagement score. So the finance employees have the highest engagement scores while the lowest is with sales, and engineering have mid level. Now we would not like to stop here. We'd like to see in more detail what is causing this disengagement or lower engagement levels. So to examine in more detail, we'll probably create a new variable. We'll create a variable called disengagement, and this variable is 1 if the satisfaction or engagement score is less than 3. Otherwise, if it is more than 3, it is more than 3, then 0. So we'll create this disengagement variable. So let's create this survey disengaged, and like we said in this variable, now before creating, first we'll analyze the data. So survey, and inside survey we'll create this. So mutate command would be useful. So with this mutate command, we'll create this disengaged variable, and in this engaged variable, we'll use this our typical if else command, if else. Now, if engagement score is less than equal to 2, which is same as less than 3, then we'll use a value of 1 else 0. Now, this is a very useful command, and you can see now this is printed. In fact, rather than printing it because we want to create a new data for our analysis, so we'll create this survey underscore disengaged and assign this. So now I can print it. I can very well print it also if I need. This is a survey disengaged variable we have created, which has one additional disengaged variable, which takes a value of 0 for higher engagement levels of 3 and more, and takes a value of 1 for lower engagement levels of employee, which is lower than 3, which is 1 or 2 and so on. So now we have created this disengaged variable in our data. In the next set of videos, we'll examine in more detail about the reasons of this disengagement, its distribution across departments, and so on. In this video, we'll continue with our exercise of employee engagement. So in the next step, we'll examine each department, compare their disengaged employees, percentage of disengaged employees for each department, the salaries, and the vacation days. So these probably are the relevant variables to be examined. So for each department, we'll compare the percentage of disengaged employees, average salaries, and average vacation days taken. Now, so the first step is to examine the summary. So first we'll use this our survey disengaged data that we have created. In this disengaged data, we'll first group it by department. So that is one good thing. We can go inside the data, group by department, Now, once we have grouped it, we need to summarize by certain parameters. So what are those parameters? First, percentage disengaged. And here we will use our summary command, summarize. So we'll have percentage disengaged. Now that is equal to mean of disengaged. That is one. Then we'll also calculate average salary as mean of salary. That is one. And then lastly, but importantly, average vacation days taken, average vacation days. So these average vacation days equal to mean of vacation days taken. So this is our overall important data points we can see here, but I would not like to not only calculate this, but also create a variable for this for future analysis. So let's call it survey summary, and I'll assign this entire data into this variable. Now let's print this and make inferences out of this. So if I print this survey summary data, you can see here. Now, the highest disengaged level, as we already saw, is in, you can see here in sales, lowest is in finance. So you recall we have changed our variables now. The disengagement variable is now, the interpretation is different. So the lower the level means more engaged. So engineering is the most engaged. And in fact, finance is most engaged, I would say. The sales have the highest value. That means they are most disengaged. And you can see their salary levels in terms of salary, if one thing, then salary is lowest for engineering and highest for finance. So salary seems to have some connect, but we'll analyze it further. But sales do have high salary, but more disengagement, which is surprising. In terms of vacation days, you can see sales have, in fact, the highest is lowest vacation days. So probably that may also be a factor. While engineering has the highest vacation and followed by finance. So these are some of the factors. We'll analyze it further. So now in the subsequent step, we would like to visualize our data. So we are going to visualize and compare the percentage of disengaged, salary, vacation days, and so on through visualization, for which we need to first widen the data frame. So in the data frame that we have created, the survey summary, we need to widen the data frame in long form. So let's see how to do that. It is simple. So what you need to do is you need to use your survey summary data, and in the survey summary data, you have to use this gather. Now this gather command, the key that you want to use is measure value equal to value. So we are creating a key variable, key value, we are giving the value, and then now the variables percentage disengaged that we want to have, average salary in the long form, and we want to have average vacation days. So these are the variables we want to have in the long form. So let me show you first what it will create. So it has created the long form data. You can see department, measure, and value. But we want to create a new data. Let's call it survey gathered, because the long form. So let's call it survey gathered. And now I'll print it and summarize it, what exactly why we want to do it. So we have created this data, which is very nice for printing. It is in long form. One variable is department. Then you have measure for each department, disengaged, salary, vacation days, and their values are also there. So now this variable is ready for plotting. And why I'm saying that, because let me show you. I'll plot this data and you'll find it very interesting. So we'll plot the long form data for visualization, and our good old ggplot command will be employed now. In ggplot, we'll specify that we want to plot survey gathered, this survey gathered data. And here we need to specify the aesthetic argument. So one is the measure argument that we want to use, value, and we want to fill it with department. So department is the color that filling we want. The next step, you have to specify the object, as you would have probably already predicted that we are going to use the column geom call kind of object. And position, I'm specifying dodge. You'll understand why I'm doing this dodge position. It probably gives me more useful graph. And also I want to facet wrap it. So facet wrapping will help me getting three separate graphs so that I get a nice this thing. And measure, I'm segregating the graphs by measure, scales as free. So now let me show you. I'll enlarge the plot window. So now I'll enlarge the plot window and I'll run it and show it to you. So when I run this command, you notice now three plots are there. So why this kind of plotting? So first I have specified that this dodge command is, so for example, if I remove this position dodge, the plot would be slightly odd. You can see, which is not very useful. So that's why the dodge command. and scale free ensures that all of them have their own scales, not fixed to one particular scale, otherwise it will be problem. And now visualization is much easier. So you can see, if you look at the salary, we can easily visualize it is for the green finance salary is the highest and lowest for the engineering department, which we saw numerically. In terms of vacation days, as again we can see, the vacations are highest for engineering and lowest for sales. And in terms of disengagement, sales has the highest disengagement, while engineering and finance they have closer. So till now we have analyzed our data with descriptive measures and some basic statistical graphs and some basic descriptive measures, but we need some more rigorous evidence of this disengagement and other data in terms of statistical measures, which we'll try to conduct in the next video. In this video, we'll visualize the data. We found that salary, vacation days, and these can be the reasons of disengagement. In the previous videos, we have done data exploratory analysis, and we found that there's a difference in the disengagement or engagement levels across sales, finance, and engineering department. Now, in this video and subsequent videos, we'd like to conduct some statistical analysis to see whether that differences are statistically significant or not. So first, for this process, we'll create an in sales variable, which will segregate the employees that are from sales versus others. So we'll create a variable in sales, which will carry only sales department and versus other. So it will classify employees in sales department versus other. So we have this survey variable already. So we already have this survey variable. Inside this variable, we'll create this mutate. And now we'll create this in sales variable. This in sales variable is if is. Now here you can see if department equal to sales, then we'll give the value as sales, else other. This is first step. In the next step, we'll also ensure that we have this disengaged variable. So we'll also again the same disengaged variable we'll repeat. Disengaged, we already know its construction. So if engagement is less than equal to 2, then it will take a value of 1. So it will indicate whether employee is disengaged or not. And if I run it, yes, this provides the classification. Now no assignment has happened, no new variable is created to hold this variable. So we need something to hold this variable that we have created. So we'll give it a name, survey sales. So this is the variable that we are going to analyze. Now we are ready to conduct a t-test of means to see whether there is a significant difference in the engagement of sales and other department employees. So the command is pretty simple. All you need to do is t.test. Now here I need to make that distinction. So survey, as you'll see, survey underscore sales. This is my variable that I want to test. Dollar disengage. So this is my variable, disengagement variable that I want to compare. Now I'll see how I write this command. Within survey underscore sales, I'll use in dot sales and the employees that are from sales. So this will ensure that only those employees where in department is sales are compared. And next, a very similar kind of command, but this time others, the other department which are not from sales. So I can just write it, I can use this no or others also, but I can just type as no. So this will also do the same. I can run this command. So just one change here. So recall I used disengage variable to create those values. So disengaged variable from the sales department, those that are from sales department, and disengage. So this was slight mistake. So this should have been the disengaged variable. Now, see, recall what is there inside this engaged variable? Those zeros, ones, whether it is a disengage or engage. And what is there in sales? It's this, those that are from sales. So this will take the disengaged score of sales, those from sales, and this will take the disengaged, those from not sales. This exclamation will ensure not from sales. So now I just need to execute this command. So I'll just execute this command and let's interpret the output for a moment. You can see the mean of X, which is those from sales, is higher 0.32, and those of not from sales is 0.20. 0 is for disengage, 0 is for engage, and 1 is for disengage. So you can see here that higher score would indicate more disengagement. As we can see, there's a difference, but whether it is statistically significant or not, for that we have to look at these T and P values. The P value is pretty high, which means we are rejecting the null of equality, which means they are not equal and quite significantly different from each other. So we can say that the engagement levels, or rather disengagement level of sales department, are quite high, in fact, from other departments. So that we have confirmed. There's one more test which is called chi-square test that we'll carry out. So we'll also conduct this chi-square test for the same chi-square test of differences. And all we need to do is we'll just do chi-square dot test. But now we'll use this survey in sales variable, survey, and compare it with along the lines of disengage. So this is the typical syntax. What this command will do, it will look at the disengagement scores and tries to see whether they are different across the line. So these are different in distribution. The data assumes that they come from the same population. So the disengagement score, they come from the sale population. It will test whether the two population, one from sales, one from others, is there a difference across these population? Are they are from not coming from the sales population? So you can run it. So you can see the output in these says the chi-square is the significant p-value is significant and chi-square test statistic quite significant, which again confirms that the two population are very different in their distribution. So basically this test confirms that the disengagement scores across the two population are very different across the sales and non-sales. So now that we have seen the differences in disengagement scores across sales, we would also like to see whether the vacation days taken are significantly different from sales and others. So we are doing the same testing, but this time around, we are trying to see whether instead of disengagement, we are looking at the vacation days now. Vacation. So there is a minor change that is going to happen. We are, instead of this disengaged, we'll rather use the vacation days taken for sales versus other departments. So we'll use vacation days taken. That is our differentiating variable. And because now this is a numerical, vacation days taken, numerical variable, unlike the previous variable, this can't be, the chi-square test won't be applicable here because this vacation days is a pure number. It's not that kind of 1 0 thing. You can see it's a pure number, so the chi-square approach will not be valid. Now see, the vacation days taken are higher in other departments. The mean is around 12.6, and for sales it is 9.22. Whether this difference is statistically significant or not, it can be seen from here. It's very significant. That means the vacation days taken in other departments other than sales is very high, almost around 12.16 as compared to 9.22 in sales. So we can see two reasons. One, they are taking less vacations, and their disengagement level, sales employees are taking less vacations, and their disengagements are also not very good. So they are bad. So there seems to be some relation. In this third part, we'll do the fair pay data analysis. We are expected to analyze the data by performing the following tasks and data visualization. First, we are supposed to import the fair pay data file and find the average salary of new hires and old employees and see whether there is a statistically significant difference across these numbers. We are also expected to summarize and visualize the salary data across job levels between the new and old hires. We are also expected to perform multiple linear regression analysis of salary on new hires and job levels as categorical variables and make inferences from these results. Lastly, we are supposed to perform multiple linear regression model of salary on new hires and departments as categorical variables and make inferences from these results. In this third part of the study, we'll analyze the pay fairness. For example, if let's say the new hires are getting more pay than the old hires. So this is part 3, where we'll analyze are there any discrepancies in pay. For example, are new hires getting paid more? So these kind of questions you want to answer. Now, as a first step, we in the first question we'll load the data. So we'll go to our file tab. So in the file tab, we have already set the working directory. So we'll see whether the data is, we need to use the fair pay data here. So this is the fair pay data. We'll load the data. Now for reference, we just copy the command so that in future it is there. So this is, with this command we read the data fair pay. In fact, I'll just name the variable pay for simplicity sake. Now, first we'll have a glimpse of this data with this glimpse command. Let's see what is inside this variable data frame. So it has 5 variables and 1470 rows. First is the employee ID, one starting from 1 to 1470, their department, sales, engineering, and so on. The salary levels, new hire, and job levels. So we have these 5 variables which we are going to analyze. To begin with, let us answer the first question. Let us compute the average salaries of new hires versus old hires. So let us compute the average salaries of new hires versus old employees. So this is pretty simple. So what we'll do is we'll go in our pay variable, the pay data that we have taken. We'll group it by new hire variable. So if you recall, the new hire variable as no, which means old hires, or yes, which means new hires. So we'll group it by this variable. It's easy. Then we'll summarize our data. And like we need summarize, we'll use average salary variable. This is a new variable that we are creating, average salary. And inside that, we'll use this mean salary. So now this variable will give us the average salary. So see, the new hires are taken at 76,074, while old hires are at 73,425. Now there can be various levels, various reasons for this. For example, there are different levels. The hourly paid employees have low salaries. So if there are more hourly paid employees, hourly wage employees, then their obviously salary would be lower. If there are salaried or at a different level, their salaries would be different. So it needs some more analysis. So let's continue with our analysis. In the next question, we will try to statistically check whether this difference is statistically significant or not. We have already done this t-testing. So we want to conduct a simple statistical t-test of mean to compare whether the salaries of old and new hires is different. So let's see that. For that, we'll conduct this t-test, and we'll use pay. Now it's quite easy. All we need to do is pay dollar salary, and inside we'll have whether it is a new hire. If it is a new hire, we'll put it as yes, and because our variable is so designed, so we have to use that, and no otherwise. So we'll put no otherwise, and we'll compare the salary variable now. So you can see here when we look at the output, the mean of X, that means yes, new hires is higher, but is it statistically significant? Yes, it is. And you can see the p-value. So at least at given this T and p value is lower than 5%. So we can say at 95% confidence or 5% significance, the salary of new hires are higher than old employees at the same on average. While our result till now suggests that there is a statistical difference in salary, but it needs some more examination because within the employee there are different levels: salary, hourly wages, and senior employees. So it also needs further investigation that whether the composition of different levels or grades of employees are same in the new versus old to make a more strong statement. So that will carry out in the next video. In this video, we'll analyze the data in more detail. More specifically, we'll try to visualize our data. We'll try to plot the employee mix across different levels. So our data contains employees as hourly, salaried, and managerial levels. So we'll try to see the employee mix for across these different mixes for the two categories: new hires, versus old. So let's start our exercise. So first we'll add to the ggplot, and we already have the pay data ready with us. We need to provide the aesthetic. So x equal to new hire, fill equal to job level. So this is a starting point. Nothing will be plotted if I run this graph. As you can see, I need to add some kind of geometric object to plot. So I'll add geom bar, which seems to be more suitable. Now, if I run it simply geom bar, I can see, I can clearly see the raw count here. Now, even this part is quite obvious. You can see with raw counts that hourly wages are there. In older employees, there are a lot of hourly wages and lower number of managers and probably a higher percentage of salaried. So kind of gives an idea why the average salary of new hires is higher, because probably of the lower mix of hourly wages. You can change this, tweak this graph a little bit as well. For example, just to show you, I can play with this position argument. I can use a fill argument. So when I use the fill argument, they are scaled. So now comparison becomes even more worthwhile. So if you look at the previous graph, it may have appeared that the salaried employees are more if you look at on absolute basis. But when you do the proportionate pro rata basis, you can see the difference in hourly. You see the proportionate composition. The hourly are still higher in the older, and you can see the salaried are more in the this thing. So it gives us some idea that in, and managers are also more in the composition. So the low strata salaries, hourly wages, they are particularly high in the older employees, and that may be one of the reasons why we find this anomaly. There's also one argument you can use, dodge, so that is also helpful. So you can see when you put dodge, then clearly they are stacked together. Although this slightly the previous one was slightly probably more useful for us because we could see the pro rata composition here. So there we can make our idea. So now it slightly confuses us. So now what we need to do is we need to probably summarize the salary across new and old levels. So we not only see that aggregate, earlier we saw at the aggregate level. So now we would like to summarize the average salaries of new versus old hires across different job levels. Probably that would give us a more clear picture. So what we'll do is we'll use this pay variable that we have created. We'll group by and new hire job level. Now, now we need to summarize this. So we'll use the summarize command and average salary, which is equal to mean. Now, if I run this command, I'll get the number. But for now, as of now, this is not assigned to anything. So first let me create a new variable. So I'll create a pay underscore so that I can use in future if I need pay group variable. And now I'll print this variable pay group. So, and let's compare the values. So when I do pay group, I'll get this output. Now let us compare them. So if I look at hourly wages, compare them with the new ones, seems to be some increase. If I look at managerial level employees, so there slight increase. Whether it is statistically significant or not, that needs to be seen, but almost similar, a little bit higher. Look at salaried number, almost similar, in fact, a little lower. So, but the increase is particularly sharp for hourly wages. So probably that one point may explain a few things, but we need more statistical inferencing and some visualization to make stronger claims. So before going to the statistical testing, which will give us some evidence, solid evidence, let us visualize the data. So let us visualize the average salaries of new and old hires across different job levels. And we know the trick. We'll use our good old ggplot. And we have already created this pay group variable for this very purpose. And I'll use this aesthetics argument x equal to new hire. Y is average salary. So I need on y-axis, I need average salary. Now I can improve this graph. Probably I'll use a different color for filling. So maybe new hire. So this is my ggplot. This is ready. Nothing will be plotted because I need to specify the geometric object and so on. So probably a geom call object would be useful here. So I'll use this geom call object. And if you want separate graphs, you can use this very nice facet trap feature. So this will create separate graphs, and also I can segregate the plots by job level. So when I plot it, you can see with for separate, the facet trap is created with separate job levels, hourly, manager, and salaried. We have new hires versus old hires. So we have a very nice diagram. So let us compare. So we can clearly see the average salary for hourly is very close, almost same for managers salaried. So new versus old, there's a slight difference in that. We don't know whether it's just statistically different or not. On graphically, they appear to be very similar. But earlier we saw there are marginal differences, but those differences are statistically significant or not, that we'll see in the next video. Visually, they appear to be quite similar, but that is no guarantee because statistical inferencing is rather more solid measure. So we'll do that in the next video. In this video, we'll conduct a simple statistical test of t-test of means. T-test of means to check whether the differences across different employee mix are different for new and old hires. So this exercise is pretty simple. Let's create a new variable pay filter. So I'll create a new variable pay filter. With this variable precisely, it will capture. So let's start with the differences in hourly employees. So I'll apply a filter and I'll filter out the with job level hourly. So I'll filter out the hourly employee here. So that makes my job simpler. Now I'll do the t-test of means, and I hope we recall how did we do that. So I'll use this pay filter variable, and for salary, I want to check whether salary of old employees versus new employees at hourly level are same or not. Now here the criteria is new hire versus old hire. So if they are new hire, equal to yes, and compare them with the old employees. So old hires, I mean. So there's no. So let's do this testing and let's interpret the result. So you can see there is a difference as we saw already, but is this statistically significant or not? So it seems to be a slightly edgy case. You can see p-value is almost 8%, which means while we cannot say it is this result is significant at 95% or 99, but we can say if we want to be a little lenient, we can see that it is significant at 90% level. So this result with 90% confidence or 10% significance, we can say that there is a difference in hourly level. What about other levels? So the same code we can rehash. So this was at hourly level. Then the next level you would like to test is manager at managerial level. So let's use this manager pay. So for manager, I'll reuse the same code. I will not rewrite the same code for managers. It's much simpler. Manager level. Let's do that. So here, okay, so it's not at all. So you can see there the numbers are also close and they are not statistically significant at all. So we can't say at managerial level. That means salary remains the same at managerial level. The last one we want at salaried, guys, with salaried. So I'll just copy this salaried. So this is the third level. So there are three levels in the data: manager, salaried, and hourly. Hourly we have checked. Manager we have checked. So lastly, we would like to check at salaried level. So salaried. So I'll tweak the same code, not rewriting the code again. Here you can see the numbers are same and p-value is also not very different. So we can say it is insignificant. So our only one result was significant as it turned out, this hourly level. So there's salary differences there is only hourly level data. So our entire result was driven by differences in hourly level salaries. So new employee have probably higher salaries at hourly level. At other levels, it appears to be the same. In the previous video, we conducted simple statistical t-test of means to compare the salary levels across different job mix. We'll try to use regression analysis for the same effect to find the differences across job mix levels in terms of salaries. So we'll conduct regression analysis of salaries across different job mix. So the same result is the same analysis, but using regression analysis, we'll see the application of regression and try to interpret the output. So first we'll use the simple regression, two variable regression. So we'll call it simple. LM for linear modeling, salary, tilde new hire. So I'm regressing this on new hire. New hire is now it's a categorical variable, but I need not do anything. R will automatically convert the variable as such for me. So data equal to pay. I'll store the output. Let me summarize this and we'll try to interpret the output. Model underscore simple. Now to interpret the output, this intercept corresponds to the reference category, which is no, which is the old hires. And at aggregate level, we can see the old hires have a salary of 73,000 average and new hires have a 2,600 hire. We have already seen that this difference is driven by the hourly wages, but still the regression analysis is another approach to see that difference. Now we want to include the job level also. So for that we would use a multiple regression. Approach is pretty simple. Instead of model, let us use a different name, model multiple. And again, I'll use the simple regression analysis, salary. Now, what I'll do is in this new hire variable, I'll multiply. So this will be an interaction effect, job level. So this is an interaction effect that I'm producing. Same data equal to pay. I'll summarize the output, model multiple. Now the output is a little complex, so we need to be careful in interpreting that. First, we need to identify the intercept reference category. See, there's no hourly, so obviously it is loaded here, and also there's no here, so that means old employees. So for old hourly wages, this is the average salary. So this is their average salary for old hourly wages. Now, if you want to know the new hourly wages, it is this, and it shows that it's statistically significant also. So this is first important result. The hourly wages that are new, they have a higher salary. So that result holds. Then we want to know the other categories. For example, job level manager with no. So that means this is a managerial level salary. And we need to add this 55,000 to get to this number to get the job level of manager with older one. Now, once you have this salary, job level of manager, the new hire, it seems though the number is not statistically significant, so we can't say much, but we need to subtract from his salary, job level with manager, the new manager. So we need to subtract this number. Obviously, we know that it's not statistically significant, so this is not a very useful result. In fact, you can consider the same number. The same thing happens for job level salaried. If you add this to this reference category, you get job level salaried, but to get the job levels new salaried, it is 1,000 less than the salaried. But again, the result is not statistically significant. So even whether you add it or not, it doesn't matter. You can use the same number because they are not statistically different. So we can use the same number for them as well. The only key inference here is that there's a difference in hourly wages across new and old hirees. In the previous video, we examined the salaries across different job mixes, managers, hourly wages, salaried employees. In this video and next video, we'll try to examine the salary differences across departments. So we'll examine the salary differences across departments. So for that, first we will summarize. First we'll create a salary variable across department. So for that, we need this good old pay variable, and we need to group by. And there are two grouping variables that we are going to use. One, whether they are new and old hirees and their department. So this will help us in summarizing the data well. So if I run this command, you can see here. So nice grouping has appeared. Now we need the summary measure. So very easily I can apply this pipe symbol and use this summarize average salary equal to mean salary. So now this will do the job. It will summarize. In fact, for future reference, I'll use this as pay group data, a new pay group data. Let me print this pay group data and analyze the results. So if you look at this pay group data, you can compare engineering versus new versus old. So you can see that new employees have higher salaries. Look at finance, 75,000. They also have higher salaries, and sales, they have quite similar salaries. So key differences appear to be in engineering and finance. And we'll probably also visualize the data to have a good eye on that. So we'll visualize the average the average salaries across new and old hires for different departments. So let's do that. ggplot. Now I'll use my pay group data which I have created, and I need to specify the aesthetics argument. So x-axis is new hire and y is equal to average salary, will equal to new hire. Now this will create an empty plot. I need to specify the geometric object that I need. So I'll specify geom underscore call, and this will create the plot for me. But again, one more feature, as you would recall, facet wrap is very useful in such situations. I'll specify that I want plots to be segregated with department, and now I'll run this. Let us examine the graph visually, and you can see clearly there's a difference between engineering, this engineering salaries, finance salaries, sales salary appear to be quite similar. So visually we can clearly see that engineering, finance have clear-cut differences. New employees are getting higher salaries. But to make a more solid statistical comment, we need to do some statistical testing, which we'll do in the next video. Now that we have visualized the data, in this video, we'll conduct the statistical test of t-test of means to compare the salary of new and old hires across departments. So we'll conduct the t-test of means of salaries for new and old hires across departments. So this is simple. Let's start with maybe engineering department. So the command is simple. I'll use this pay data that we have, apply this filter. So this filter command will help us in selecting the department. So we'll select the department which is engineering. So this is one. So you can run the command, see if it is running correctly. You can save this. So let's call it pay underscore engineering. So I'll save the data here. Now, the next thing you need to do, or I'll rather use it, I'll use it because I want to reuse it. I'll use this pay filter. Now, I'll apply the t-test here. This is simple. You have to use the pay filter data that you have created. In this pay filter data, I need to compare the salaries, and salaries I need to filter out across departments. So for engineering, I've already filtered. So next is I want to filter across new versus old hires. So new hire, if it is new hire, yes or no. So I'll use yes here. Then, so you can see I'm not writing the full codes. I'm just reusing the existing codes. Here I'll type no. So I'll not rewrite the full code. All I need to do is a little bit tinkering of the code here and there, some few segments, and now run it. So let us start with this analysis. So you can see across engineering, there seems to be a difference, which we saw earlier also, but is it statistically significant? Yes. As we can see, it is even significant at 1%, or that means with a 99% confidence or 1% significance, we can say that our result is significant. Now we'll repeat the same exercise. Earlier we did it for engineering. I'll not rewrite the full code. I'll just keep copy pasting it. So engineering we have done. Let us next do it for finance. So we'll do it for finance. All I need to do is just modify the code slightly. Now, what about finance? So the difference is there, but it is not statistically significant. So it, as we can see, I ran the test, but it is not statistically significant. So the result is not statistically significant, so we can't use it, or we can't say that. Let us compare it. Although the number is material, it's quite material, in fact 4,000, but not statistically significant. Let's use the last one, which is sales, and see if there are differences across new and old hires. So let's do that. Now almost indifferent. So for say sales, it seems there's not much difference. So we can't say that. There's very significant difference across first one, which is engineering. So just to summarize this video, we conducted a t-test and we can see there is a significant difference across this engineering variable. In finance, there was difference, but it seems that it was not statistically significant. For sales, it was neither statically synchronous nor it appeared to be, so we can ignore that. In the next video, we'll further carry out this exercise with the help of regression modeling. In the previous video, we conducted the t-test to examine the salary differences across departments. In this video, we'll conduct multiple linear regression analysis to examine the salary differences across departments. Now, please recall we have already done similar exercise with multiple regression modeling with the job mix levels. The same technique, same approach we'll employ here. So I'll keep the name of the variable also similar, model underscore multiple. Now, in this linear modeling function, I'll provide the salary, which we are interested in analyzing. And then we'll use the same technique. So new hires and multiplied, because we are looking at interaction term, but this time not with the job mix, but department, and with the same data pay. So I'll store the output and summarize it. So let us examine the output now. The interpretation, the technique and approach will remain same. So you can see here sales, finance are loaded. So the engineering department is loaded on intercept, and particularly the no, that means old engineering employees, their value is the reference value. So this reference value can be ascribed to the old engineering department. Now look at the new ones. For new hires, there is a significant difference. So we can say between engineering department old and new hires, there is a significant difference. Now let's suppose you are looking at finance, and this is for old ones. So first and foremost, you need to add the finance with the intercept with the reference category to get the old employee salaries in finance. If you want to compare with the new salaries, you need to further look at this. So you need to add this number, but please recall it's not significant. So the difference is not significant across finance. Across sales, it is significant. This is the same finding that we saw earlier, quite a little bit similar. So across sales and engineering, there is difference which seems to be, in fact, for sales, if I look at compared with, it's not. So only one department. So only with intercept, with respect to intercept, only one engineering department, while sales is significantly different from the reference category. But if you compare it old and new, for new hires versus old hires in sale, it is not. So we can't say that. So we'll still stick to the earlier finding that we had earlier. That means our t-test result is still hold, that we are saying, concluding that the difference is only across engineering department.